Now, it would be an extreme challenge to say which body system is the single most important system in the body. Cardiovascular system comes to mind because we need to deliver oxygen and nutrients to our tissues. But then again, if we didn't have the respiratory system, we didn't get that oxygen. The brain obviously is huge. I'm not saying physically, which it is, but its importance because it regulates just about everything in the body, including heart rate. So it's coupled to the cardiovascular system. But one could easily argue that the renal system is the single most important system in the body. Now, to be clear, it's totally lame to suggest any system is the most important system because the body works holistically together and not separately. But without the renal system, everything else is out the door. To be clear, if anyone has ever known anyone that has to go to dialysis 2, 3, 4, 5 times a week, that should tell you how important the renal system is. So the renal system is composed, gross anatomy at least, 2 kidneys that sit in the retroperitoneal space and a urinary bladder that resides within the pelvic girdle, delivering urine from the kidneys to the urinary bladder are ureters. So there's going to be 2 kidneys, 2 ureters, and 1 bladder, and then eliminating urine from the body from the bladder is going to be the urethra right here. So 2 kidneys, 2 ureters, bladder, and 1 urethra. Overall functions of the renal system, I've simplified it dramatically. If you look in textbooks, there's a long list of things, but I'm going to simplify it to filtering blood plasma and regulating blood osmolarity. So filtering blood plasma, what does it filter? It filters everything but blood cells and plasma proteins. So one would describe the renal system filtering blood plasma with the exception of most plasma proteins, which are too large to get filtered. Now, regulating blood osmolarity. So keep in mind that requires us to know what the plasma is composed of. Certainly the majority of it is water. There's a lot of nutrients in it, amino acids, lipids, glucose. There's hormones. There's waste products like urea and uric acid, and a bunch of ions. And it's not limited to that, but that's a good start for our discussion here. So everything I just described that was filtered, some of those things the body actually wants back. So the nephrons, which are the functional unit of the kidney, do all the work. This big structure right here is a nephron. We'll talk about that in a minute. But the nephrons are going to filter a bunch of stuff from the blood plasma and then immediately reabsorb some of that back into our bloodstream so we don't eliminate it from our body. We will talk about that. Now, as far as regulating blood osmolarity goes, this is part and parcel to regulating blood pressure and blood volume. Blood volume is intimately or directly related to blood pressure. And related to that are solutes, or the osmolarity of our blood. So without enough solutes in our blood, we're not going to draw water into our blood. With limited water in our blood plasma, that's going to decrease blood pressure. The corollary is if we have high blood pressure, we probably need to get rid of some of the solutes within the blood. And then that can be moved into the nephron. The functional unit of the kidney are the nephrons. There are roughly 1 million nephrons per kidney. This kidney over here, I am exhibiting a coronal section or a frontal section of the kidney. So we're looking at the posterior half of that kidney. And this allows us to see the interior. And what's important to us is the outermost part of the kidney is known as the renal cortex. Renal refers to kidneys. We could call this the urinary system as well. So this is the renal cortex, and this is the renal medulla. The nephrons reside in the renal cortex. Some of them have a component that dips down within the renal medulla. So if we take a closer look down here at a nephron, the nephron is everything in green. I have some blood vessels included in here, which have to be part of this discussion because the nephrons don't work in the absence of these blood vessels. But to be clear, the nephron is only what I have drawn in green. So we have Bowman's capsule right here, which leads to the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, and then the collecting duct. To be clear, a nephron doesn't really look like this. It looks more tortuous, wound up, and actually very hard to decipher what's going on with it. So it is typical to draw a nephron kind of spread out like this so we can really discern all its components. So, like I said, we need blood vessels associated with the nephron. The major blood vessel, maybe I shouldn't say major, a significant blood vessel is what's known as the glomerulus. And that's what I have drawn in purple right here. It is a capillary bed. Full disclosure, the renal system has some of the most challenging words in anatomy and physiology to pronounce. The glomerulus is probably the top of that list. And I can only say it because I've tried, because I've been practicing for many, many years. So we have the glomerulus right here, which is a capillary bed or tuft of capillaries that is encapsulated or surrounded by Bowman's capsule. Sometimes I may utilize the term renal corpuscle, and the renal corpuscle includes both the Bowman's capsule and the glomerulus together. So if this is Bowman's capsule, this is the glomerulus inside of it. Collectively, sometimes we refer to that as the renal corpuscle. Bringing blood into the glomerulus is the afferent arteriole. Taking blood away from the glomerulus is the efferent arteriole. To be clear, I'm probably not pronouncing those how they should be pronounced. They are probably the afferent and efferent arterioles. But to distinguish or be very clear what I'm talking about, I tend to refer to this one, which is bringing blood into the glomerulus, as the afferent arteriole, and the efferent is taking blood away. So let's put arrows in there just to solidify what I just said. Afferent taking blood into the glomerulus, efferent taking blood away. Now, you may notice that this is very atypical of what we find in the body. Generally speaking, in the body, we find arterioles entering capillary beds and venules taking blood away from capillary beds. This is a unique setup known as a portal system, where between two arterioles we have a capillary bed. But then we have another capillary bed right here known as the peritubular capillary. The peritubular capillary is merely the extension of the efferent or efferent arteriole. Let's take a look at some of the physiology involved with the nephron. So we have what's known as the glomerular filtration rate. This is the rate at which blood plasma is filtered into the nephron. And when I say nephron, I'm really saying all 2 million nephrons, because there's roughly 1 million nephrons per kidney. We want the glomerular filtration rate to be approximately 125 milliliters per minute. And it's pretty important that it's regulated fairly close to that. If we look at some numbers, 125 milliliters per minute, multiply that by 60 minutes per hour, 24 hours per day, and then 1 liter for every 1,000 milliliters. If we're to cancel out all the zeros, all the units, we're going to be left with 180 liters per day. That is to say, based on a GFR of 125 milliliters per minute, is going to equate with the production of 180 liters of filtrate created every single day. And that's huge. That's at a dramatically large amount of filtrate that is being produced. Why would I say that? Well, how much blood plasma do we have? We have only 3 liters of blood plasma in our body. If we only have 3 liters of blood plasma in our body, how in heaven's name are the kidneys and the nephrons producing 180 liters of filtrate every single day? To be clear, I haven't defined filtrate. Filtrate is a substance that leaves the circulation, leaves the glomerulus, and moves into Bowman's capsule, moves into the nephron. So once again, how could we possibly filter 180 liters of blood plasma every single day if we only have 3 liters? That's because our kidneys and our nephrons filter our entire blood plasma 60 times per day. 60 times 3 is 180. So our blood is constantly going through these nephrons every single day, filtering our blood, making sure we're getting rid of waste products, getting rid of hormones, and certainly probably reabsorbing substances. It also might be getting rid of water. We might be reabsorbing water back into our bloodstream. So if we are creating 180 liters of filtrate per day, we are certainly not producing 180 liters of urine per day. We're really only producing on average about 1.5 liters of urine per day. That means this is probably less than 1% of 180. So what happened to the remaining, which I believe, if my math is right, 178.5 liters of filtrate? It is moved back into our blood plasma, and we'll talk about how this happens. That's known as reabsorption, moving substances from the filtrate, which is in the nephron, back into our bloodstream. Now, I'll argue all day this is an imperfect system. If it was a perfect system, the nephrons would only filter out only what we need to get rid of, but that's not how it works. So once again, the remainder gets reabsorbed. So once again, we're gonna eliminate or urinate out roughly 1 liter to 1.5 liters per day. And that urine is highly variable. It could be super concentrated at roughly 1,200 milliosmoles per liter, or it can be super dilute at 50 milliosmoles per liter. Keep in mind our blood plasma is roughly 280 to 300 milliosmoles. So the filtrate varies between 50 and 1,200. If we have concentrated urine, that means we have reabsorbed most of the water and it is concentrated in solutes. If it is dilute or clear, that means we're getting rid of water. What sort of pathological conditions result in these urine concentrations? Well, if we have high blood pressure, the body may be trying to eliminate fluid volume from our blood vessels to decrease pressure, or pharmaceuticals may do that. And if we have super highly concentrated urine, maybe we have low blood pressure or we're severely dehydrated. So let's take a closer look at the nephron. Here's an expanded view of the nephron: Bowman's capsule, proximal convoluted tubule, loop of Henle, distal convoluted tubule, and the collecting duct. So there are a number of processes that happen within the nephron or in conjunction with the glomerulus, which we see right here. That's going to be the afferent arterial, efferent arterial, peritubular capillary. So one of the activities or functions of the nephron is filtration. And I shouldn't say just the nephron, this is the renal corpuscle, because we can't have filtration without the glomerulus as well. So filtration is the movement of components from our blood plasma directly into the nephron. The nephron is one big tube, which I'm trying to show right here. This is the lumen of the nephron. So filtrate passes all the way through the nephron. And to be clear, I have the filtrate drawn in red, which I probably shouldn't, because that may suggest that there's red blood cells in it. There is not. I've just drawn it in red because I think we can see red much better on the video than we can see a yellow or orange marker. So this is filtrate. Once the blood plasma moves into the nephron, we refer to this as filtrate. And once again, filtration is movement of blood plasma minus the plasma proteins into the nephron, from the blood into the nephron, specifically in Bowman's capsule within the renal corpuscle. Another process that occurs is reabsorption, and that is taking components of the filtrate that our body actually wants back and puts it back into the circulation, moving it from the nephron into Bowman's capsule. Scratch that. From the nephron into the peritubular capillary. The great majority of reabsorption occurs in the proximal convoluted tubule. As a matter of fact, by the time we get to the end of the proximal convoluted tubule, the nephrons, all 2 million of them, have reabsorbed 75% of the filtrate. To be clear, reabsorption happens along the whole continuum of the nephron, but the great majority of it occurs in the proximal convoluted tubule. Another activity we have is secretion. And secretion is a means really of fine-tuning our filtrate Like reabsorption, secretion can happen anywhere and does happen anywhere along this continuum, but the fine tuning of our filtrate occurs mostly in the distal convoluted tubule. Secretion is movement from the blood, specifically the peritubular capillary, into the nephron. From the peritubular capillary into the distal convoluted tubule. Once again, it doesn't always have to be into the distal convoluted tubule, but in this image, that's what I'm showing right here. So one take-home message here is that secretion and filtrate are both moving in the same direction. That is to say, they are moving substances from the blood into the nephron. Secretion from the blood into the nephron, and filtration from the blood into the nephron. Whereas reabsorption is moving from the nephron back into the blood or back into the circulation. One thing I want to point out is, why is it called reabsorption? Because if we look at glucose, for example, which often gets reabsorbed in the proximal convoluted tubule, glucose was originally absorbed via our GI tract into our bloodstream. We consume a bunch of glucose, and then it gets absorbed into our bloodstream. So then it's traveling through the body, and at some point it may get filtered from the blood plasma into the nephron, but then the nephron says, actually, we want that back in the blood. So it is absorbed once again back into the bloodstream. This equation right here, E equals F minus R plus S, it allows us to determine how excretion or urine is produced. That is to say, it's everything that is filtered into the nephron minus whatever is reabsorbed plus whatever is secreted. Once again, filtration and secretion are moving in the same direction. So once I've already really answered this, what gets filtered? Everything in the blood plasma except plasma proteins. And to be clear, blood all flows together, the blood cells and the plasma, so it's not really separated. But when I say everything in the blood plasma, I am not including red blood cells, I am not including white blood cells, and I'm not including platelets. It's everything in the blood plasma gets filtered with the exception of the large plasma proteins. How is GFR modified? That is to say, if we are not at 125 milliliters per minute, the nephrons need to do something. Something needs to happen to get it back up or back down to 125 milliliters per minute. Filtering, having a GFR higher than 125 milliliters per minute is as problematic as having one that is too low. So there's pressure within the glomerulus like there is in any capillary bed. And if GFR is too low, somehow we need to raise that pressure there. If the body dilates the afferent arteriole, making the afferent arteriole larger, if we make this larger, then we're increasing the volume of this container, decreasing the pressure, and by decreasing the pressure here, we are going to increase blood flow into the glomerulus. Another thing that could happen is constriction of the efferent arteriole. By constricting the efferent arteriole, that will back up blood or flood blood or kind of dam up the exit of blood from the glomerulus to increase fluid volume in here. If we increase fluid volume in the glomerulus, either by dilation of the afferent arteriole and or constriction of the efferent arteriole, that's going to increase fluid volume in the glomerulus. And if we increase fluid volume, that's going to result in an increase in pressure and bring GFR back to where it needs to be. Now, to be certain, there are 3 pressures that we need to talk about in relation to the renal corpuscle. There is our glomerular pressure, and that is merely the blood pressure within the glomerulus, and that is established by systemic blood pressure. We also have capsular pressure. When I say capsular, I'm talking about Bowman's capsule. And when filtration occurs, fluid is moving from the glomerulus into the capsule. And as fluid volume increases in the capsule, keep in mind, Bowman's capsule is a container. And as fluid volume increases in that container, it's going to have a corresponding increase in pressure. So we're going to have pressure moving out of the glomerulus, or let me rephrase it, pressure causing blood plasma to be filtered out of the glomerulus. But then we're going to have a corresponding pressure in the capsule, which is kind of going to try to move that blood back into the glomerulus. There's another factor that is somewhat trying to move filtrate back into the glomerulus, and that is colloid osmotic pressure. We talked once before in the cardiovascular system, at capillaries, we lose a bunch of fluid volume in the capillaries, but on the venous end of the capillaries, that water goes immediately back into the capillary due to the high concentration of plasma proteins. So these plasma proteins that don't get filtered are trying to suck that water back into the glomerulus, and that's what we refer to as colloid osmotic pressure. So capsular pressure and colloid osmotic pressure are both trying to move filtrate back into the glomerulus. Now, I'm not suggesting none of it's going to move downstream, but keep in mind we have a container right here that is interfacing with the glomerulus. And glomerular pressure is trying to move filtrate or blood plasma into the nephron. As long as glomerular pressure is greater, and this arrow is showing going this direction, as long as glomerular pressure is greater than these two opposing pressures, then we're going to have the net movement of blood plasma or filtrate into the nephron. And the last thing to show here is just excretion, that is filtrate being eliminated from the nephron. Once filtrate leaves the collecting duct, it's now known as urine. It, truth be known, doesn't go immediately from the collecting duct into a toilet or behind the bush or wherever this is going to happen. But this is going to move into the renal medulla, eventually into the renal calyces, renal pelvis, into the ureters, into the bladder, and then excreted. Okay, let's talk about how things get reabsorbed from the proximal convoluted tubule back into the peritubular capillary, back into circulation. This is what's going to be known as bulk reabsorption. So to put all this in perspective, these are the tubule cells of the proximal convoluted tubule. Just like all these cells right here are lining the proximal convoluted tubule on the bottom and top right here. These are all simple cuboidal cells. To be clear, the whole nephron lining the lumen is covered with epithelial cells, specifically simple cuboidal. Not all of it's simple cuboidal. There is some simple squamous here and simple squamous up in Bowman's capsule. But what I'm showing in this image over here, I'll get back to this in a second, is that this right here are the epithelial cells that I'm trying to show. So we're really going to focus on just one of them. This is the lumen. So once again, this is the lumen right here. This is one of the tubule cells, the one on the top. Here's the peritubular capillary. So one thing to keep in mind, when filtrate enters Bowman's capsule, it tends to be isoosmotic with blood plasma. That is to say, blood plasma is about 280 to 300 milliosmoles, as is the filtrate. Which means when we're trying to figure out how things move into these tubule cells and then across into the extracellular fluid, we can initially think of it very similar to all cells in the body, like we've been talking about for a long time now. That is to say, a high concentration of sodium outside of cells, low concentration in, high concentration of potassium inside of cells, low concentration in. High concentration of potassium there, low concentration of sodium here. One thing I want to point out, this surface right here is known as the apical surface, and this surface up here is known as the basal surface. Any surface of epithelial cells that face a lumen is the apical surface. Okay, so let's just look at sodium for a moment. Sodium is going to move from an area of high concentration into the lumen, let me rephrase that, from the lumen into the cell of the nephron, or of the proximal convoluted tubule. To be clear, that is no different than what happens throughout the body. High concentration of sodium to low concentration. That sodium can then move into the extracellular fluid or cross the basal surface of this cell via the sodium-potassium pump. That's generally, dare I say, always how sodium leaves cells, via the sodium-potassium pump, because it's moving against its gradient to an area of higher concentration out here. Now, to be clear, why isn't sodium moving from here to here down its gradient? Merely because there's no channels available for it to pass through. When I say available, they don't exist. Specifically, because we don't want sodium crossing the basal surface. And sodium's not moving from here into the lumen because it would be going against its gradient. There's a super high concentration of glucose in the cells of our nephrons. And that's because they are very, very highly metabolic. That is to say, they're using a ton of ATP moving things against their gradients. So we need a lot of glucose in it. Which means if we're trying to move glucose, C6H12O6, into this tubule cell, it's going to be moved against its gradient, and that's going to be achieved via the sodium glucose transport, which is moving sodium against its gradient into the cell with the help of the kinetic energy of sodium moving down its gradient. Once again, the kinetic energy of sodium moving down its gradient is going to pull glucose against its gradient into the cell. Then all glucose needs to do at this point, because there's a high concentration in the tubule cell, is move a glucose transporter. This is just a GLUT channel right here that glucose passively moves through into the extracellular fluid and into the blood plasma. And this sodium, the sodium certainly could be going this direction via a leakage channel. All the sodium that moves into the tubule cell is going to get pumped out via the sodium-potassium pump, and then potassium is coming in, and then potassium could immediately leave via potassium leakage channels. Now, once sodium and glucose leave the filtrate, move into here, and then move into here, that's going to be a lot of solutes that are moving across this tubule cell and into the extracellular fluid. And then water will chase solutes. So water is probably going to go via the paracellular pathway between cells. So water is going to chase solutes into the extracellular fluid, then into the blood. Now that we've lost a lot of water, so initially I should say potassium's not being reabsorbed, passively at least, because there's a low concentration of potassium in the filtrate, just like we have in the extracellular fluid, and a high concentration of potassium here. But once we lose all this water from the filtrate, now our filtrate is extremely concentrated in solutes, including potassium, which now may have a higher concentration in the lumen than in the cell. So if there are potassium channels right here, then potassium will move into the cell across the apical surface and basal surface, but more likely it's going to move via this paracellular pathway, just like water. So potassium will eventually have a high concentration within the lumen, which will facilitate its reabsorption. So this is just one look at how things are reabsorbed in the proximal convoluted tubule. It's known as bulk reabsorption, and we'll take a closer look at all of this in the next video.